The name Chernobyl echoes through history, a chilling synonym for nuclear disaster. But beneath the layers of human error and geopolitical context lies a stark engineering truth: the catastrophic meltdown of Reactor No. 4 was fundamentally rooted in a design flaw. This isn't just a story of a single accident, it's a forensic examination of how the very physics intended to control a reactor instead propelled it towards destruction, altering the course of nuclear energy forever. We dissect the specific design choices that turned a planned safety test into the ultimate failure, unraveling the mechanics of a catastrophe. At the heart of the Chernobyl plant lay 4 RBMK-1000 reactors, a Soviet-designed graphite-moderated, light water-cooled power reactor. Unlike most Western reactors that used enriched uranium and relied on water for both cooling and neutron moderation, the RBMK design allowed for the use of natural uranium, offering significant economic advantages. This choice, however, introduced inherent complexities. The RBMK was a pressure tube reactor, meaning its fuel assemblies and coolant flowed through thousands of individual vertical tubes embedded within a massive graphite block, a configuration that would prove critical in its undoing. The use of graphite as a neutron moderator was a defining feature of the RBMK. Its purpose was to slow down the high-energy neutrons released during fission, making them more likely to split other uranium atoms and sustain the nuclear chain reaction. Graphite is an excellent moderator, highly efficient at slowing neutrons without absorbing too many, which allowed the RBMK to operate with less enriched fuel. But this choice also meant that, unlike water-moderated reactors where the coolant also acts as a moderator, the RBMK's moderation wasn't tied directly to its coolant. This decoupling was a key factor in its instability. Central to the Chernobyl disaster was a physics phenomenon known as the positive void coefficient of reactivity. In many reactor types, if coolant water turns to steam, the steam displaces water, and since water also moderates neutrons, reactivity decreases. This is a negative feedback loop, inherently safe. The RBMK, however, was different. Because graphite handled most of the moderation, if the light water coolant boiled into steam, creating voids, fewer neutrons would be absorbed by the water, and more would be available for the graphite to moderate. This increased the rate of fission, creating more heat and steam, further increasing reactivity. A runaway chain reaction. The RBMK's positive void coefficient was particularly dangerous at low power levels. At higher power, there were enough steam bubbles already present that the void coefficient's effect was partially masked. However, when the reactor operated at low power, below 700 MWth, neutron absorption in the water coolant played a more significant role in reactivity balance. A small increase in steam bubbles could then dramatically reduce water's neutron absorption, leading to a much larger and faster surge in reactivity. This made low-power operation inherently unstable and prone to uncontrollable power excursions, a fact that was inadequately understood by operators. On April 26, 1986, the crew of Chernobyl Unit 4 prepared for a routine safety test. The objective was to determine if the reactor's residual rotational energy in the turbine could power critical safety systems during a blackout, providing backup cooling for a brief period until diesel generators could kick in. To perform this test, the reactor's power was deliberately reduced to extremely low levels, far below the safe operating minimum, pushing the RBMK into its most unstable regime. This decision, combined with disabled safety systems and an incomplete understanding of the reactor's behavior, set the stage for catastrophe. Driven by a desire to complete the test without interruption, the operators intentionally disabled several critical safety systems. Automatic shutdown mechanisms designed to prevent operation at low power or with insufficient cooling were bypassed. Emergency core cooling systems, which would have injected water into the core during a power surge, were also switched off to avoid skewing test results. This left the reactor effectively blind and unprotected, allowing it to drift into a highly precarious state where human intervention was the only remaining safeguard, a safeguard that was about to be catastrophically tested. As power levels became erratic and began to rise uncontrollably, the shift supervisor, Akimov, made the fateful decision to activate the AZ-5 button, the emergency scram. This button was designed to initiate a rapid shutdown of the reactor by fully inserting all control rods into the core, absorbing neutrons, and stopping the chain reaction. It was the ultimate safety measure, intended to halt any dangerous power excursion. However, in the RBMK 1000, even this failsafe had a critical design flaw, one that would not only fail to prevent the catastrophe but actively accelerate it. The RBMK control rods were made of boron carbide, a neutron-absorbing material, designed to halt fission. But crucially, the ends of these control rods were tipped with graphite sections, approximately 1 meter long. When a control rod was fully withdrawn from the core, its tip rested just outside the active fuel zone. Upon activation of AZ-5, the first meter of material entering the core was not the neutron-absorbing boron carbide, but this graphite displacer. This design was intended to improve neutron flux distribution during normal operation, but its consequence during an emergency shutdown was devastating. When AZ-5 was pressed, the graphite tips of the control rods began to descend into the reactor core. As these graphite sections entered the channels, they displaced the neutron-absorbing cooling water. Since graphite is a moderator and not an absorber, this initial action had the perverse effect of increasing reactivity. Instead of immediately shutting down the reactor, the first few seconds of control rod insertion caused a localized power surge in the lower core. This positive scram effect was a critical design flaw, essentially adding fuel to the fire at the very moment maximum control was needed. With the graphite tips displacing water and initiating a surge, the positive void coefficient kicked in with terrifying speed. The sudden increase in power caused a massive, instantaneous boiling of the remaining water coolant in the pressure tubes. More steam meant more voids, which in turn meant even higher reactivity due to the RBMK's design. This created a rapid, exponential power surge. Within a mere 3 seconds, the reactor's power output jumped from its already dangerous low levels to approximately 100 times its rated thermal output, completely overwhelming the reactor's capacity and integrity. The unimaginable power surge led to a rapid, violent generation of steam. The pressure inside the thousands of individual fuel channels became immense, far exceeding the design limits. At 1:23:47 a.m., the first explosion ripped through reactor number 4. This was a steam explosion, not a nuclear detonation. The rapidly expanding superheated steam tore apart the fuel channels, shattered the core, and lifted the 2,000-ton concrete upper plate of the reactor, known as the upper biological shield. This event exposed the reactor core to the atmosphere, initiating the catastrophic release of radioactive materials. Moments after the initial steam explosion, a second, more powerful blast occurred. With the pressure tubes compromised and the core exposed, air rushed in, reacting with the superheated graphite moderator and zirconium cladding. This chemical reaction generated explosive hydrogen gas. This second explosion, a thermal explosion caused by the hydrogen and other superheated materials, completed the destruction of the reactor building. It expelled massive amounts of radioactive fuel fragments, graphite, and other core materials high into the atmosphere, creating the infamous plume that would spread across Europe. The reactor was now an open, burning wound. A critical design difference between the RBMK and many Western reactors was the absence of a robust containment building. Western reactors typically feature massive, reinforced concrete containment structures designed to withstand internal explosions and prevent the escape of radioactive materials in the event of an accident. The RBMK, however, was housed in a conventional industrial building. This lack of a secondary containment meant that once the reactor core was breached, there was no physical barrier to prevent the escape of radioactive contaminants directly into the environment, accelerating the spread and severity of the disaster. Beyond the engineering flaws, Chernobyl exposed a chilling systemic failure of safety protocols and a culture of secrecy. Critical information about the RBMK's positive void coefficient and the control rod tip design flaw was not widely disseminated to operators, or was downplayed. There was a pressure to meet production targets and complete tests, often at the expense of safety. This created an environment where operators were ill-equipped to understand the dangers of their own equipment, leading to a cascade of errors and an inability to recognize the signs of an impending catastrophe until it was far too late. Post-disaster investigations were a monumental task of forensic engineering. Teams analyzed core samples, seismic data, radiation patterns, and eyewitness accounts. They meticulously pieced together the sequence of events: the initial power reduction, the disabling of safety systems, the fatal AZ-5 button press, and the design flaws that turned a routine shutdown into an accelerant for disaster. The analysis conclusively pinpointed the positive void coefficient and the graphite-tipped control rods as the primary engineering culprits, exacerbated by the operational choices made under pressure. This deep dive into failure became a blueprint for future safety. Chernobyl reshaped the future of nuclear energy safety worldwide. The catastrophic event spurred an unprecedented international effort to improve reactor design, operational procedures, and safety culture. Reactor types with positive void coefficients were scrutinized, and RBMK reactors that continued to operate underwent extensive modifications to mitigate this risk, including enriching the fuel and adding more neutron absorbers. The incident led to the establishment of stricter international safety standards, enhanced transparency, and improved emergency response protocols, moving the industry towards a more robust, safety-first paradigm. The legacy of Chernobyl is a somber reminder of the profound responsibility inherent in harnessing atomic power. It stands as a stark lesson that even the most advanced technology can be undone by fundamental design flaws, compounded by human error and systemic organizational failures. The forensic engineering analysis of Chernobyl provides invaluable insights into the complex interplay of physics, mechanics, and human factors. It pushed the nuclear industry to confront uncomfortable truths, leading to crucial advancements in safety features, operational training, and regulatory oversight, ensuring that such a combination of catastrophic flaws might never again align.